Let's keep going on with what we have started yesterday. Which was about how photons. So we are looking at how particles interact with radiation, and we started from the process of pair production, which is particularly important for extragalactic photons that have to travel to Earth. And while traveling to Earth, they can produce pairs. And so there is a finite probability, if you want, a survival probability for a high energy photons to arrive to us, which depends on the initial energy of the photon and the redshift at which the photon was produced. So this survival probability is what we call optical depth, and we have seen yesterday how to derive it from the cross-section. So this is a function in general of the cross-section for pair production, and also the energy density of the photon fields, which is the target for this interaction to happen. So the effect on fluxes of high energy sources of this absorption term is to reduce the intrinsic photon flux by an exponential factor, which depends on this optical depth. And we have seen yesterday that depending on the energy of the incoming photon, there is a maximal probability for the photon to be absorbed on different parts of the radiation field. So in particular, if you have TV photons, that will get maximally absorbed by optical radiation. If you have PV photons, they will get maximally absorbed by the CMB. So there are several reviews about this kind of process, and I quote a few of them in the slides. So this is how this optical depth evolves with energy of the photon field, and the different lines that refers to different redshifts at a very high energy. Mostly is the scattering onto the CMB, which is what we have seen also yesterday. So when the optical depth is equal to 1, this defines what we called gamma ray cosmic horizon, which is a measure, like an indicative measure of what is the distance traveled on average by photons of different energies in the extragalactic radiation field. So if you take Z0 to be the redshift of the source, then if the redshift is not large, so you can approximate the distance, the effective distance with the redshift through the Hubble law. And then you have directly a relation between the distance that can be spun by those photons and their redshift. And you end up having a plot as the one shown here, where Z of the source is our Z0, and the distance is the distance to the source. So those different lines here defines equal values of taus for different energies, observed energies, which is what we call E gamma in my notation here. So anything that has a tau above 1, so an optical depth above 1, is absorbed. And here is the transparency window of photons. So in other words, you can always compute what is the distance or what is the cosmic ray, the gamma ray horizon in the universe, and you see that there is a maximal absorption for photons of about 10 to the 6 GeV, while at lower energies, basically, you have photons that are freely propagating. So this gives you the maximal energies and the maximal distances at which you can see photons from far distant sources. So it means that the universe is opaque to gamma rays that comes from very far and from high redshift sources, especially at the highest energy. So this one can also compute for an average source spectrum that there should be a cutoff in the energy spectrum. So this, this parametric behavior here induce, if you have, let's say an initial power law of the intrinsic spectrum, then as a matter of fact, you will see a third, a spectrum which is a power law with an exponential cutoff. And so the typical cutoff energy at which you have this exponential depletion can be approximated as a function of the redshift to the source. And you see that if you have sources that are local, then the cutoff energy is about 800 GeV. But if you have farther away sources, then the cutoff energy will change. So depending on the redshift of the source, then you are sensitive with different instruments to different redshift bins. Because at certain point, you won't see any longer your source in your energy band because of this exponential cutoff in energy. Is minus 2.4. No, so the cutoff energy, you can rewrite this as energy to the alpha times an exponential of minus energy divided minus energy of the cutoff, and this is this cutoff energy. So if you want, is a parametrization, is an effective parametrization of this absorption term. So what people have done in the past, and a group from has a paper about that, was to use high energy gamma ray emitters, extragalactic ones, to try to measure this cosmic ray gamma ray horizon. So here the points are the measurements from using data of high energy emitting sources, mostly blazars, as seen by the LAT telescopes. And here, the red band is the prediction that you have from a typical model of extragalactic background light and what you would expect for this cosmic ray gamma ray horizon given the model of the radiation field. So the way in which these data points are derived is to find like a measure or a definition, an effective definition of the optical depth that starts from the observation of the spectra of high energy sources. And in particular, so how they define. Is there a question? I don't remember what alpha I wrote yesterday. This was the no. This is just whatever. It's just a power law, so which is a fit, to the data. Yes. So the way in which those points are defined is by having a measure of the absorption of the optical depth by basically using the ratios between the intrinsic flux and the observed flux. And as you see, there is a dependence on the intrinsic flux, which is not known. So you have to make assumptions on this power law and how the reconstruction of FBL of the optical depth changes with the intrinsic spectrum of the source. And sometimes you can even use data at lower energies to fix the power law of your emitting source in order to get rid of the dependence from this unknown parameter. So this is just to summarize. So typically what you expect is a power law from a highly emitting source, like a blazar, and then what, as a matter of fact, what you measure is this modified spectrum because of the optical depth and the pair production. Something that I mentioned yesterday is that whenever you have this pair production, that these pairs are injected into the extragalactic space, and so they still can produce gammas, and they initiate what we call the electromagnetic cascades that gives a secondary component of photons at lower energies, because the energies of the pairs and the following gammas are less than the incoming photon and the primary photon. So if there are no questions about this point, yeah. Yeah, that's the definition. So the so when I say when we say horizon, typically we mean a distance. But but you can have an horizon in Z or D equivalently. Yes. So also this relation only holds if Z is less than 0.1 or 0.01. Yeah, sure. Yeah, because this is you can think about, depends. There are three quantities that are related. One is the energy of the photon that can reach us. One is the redshift, and then redshift and distance are linked, right? So it depends what you mean. Here is clearly the horizon, energetically speaking. You can plot if you want. Here are the three axes. So you can look in whatever direction. The most important thing is that you have a relation between the maximal energy that can reach us from a certain distance or from a given redshift. So you have no arbitrarily high energies that can reach us if the source is very high. So yeah, there is an horizon in three directions. Okay. Let's then move to another big and important process, which will take us quite some time today, which is the inverse Compton scattering. So this is a process that is the most relevant for producing photons at MeV to GeV energies. So the idea is that you can look at it as a standard, like QED two-body scatter between an high energy electron and the photon. And this is an elastic process that gives you a final electron again and a photon whose energy will change because of this scattering and interaction. So it's called the inverse Compton because we consider the electron as the projectile and the photon as a target. And we can look at it from different angles. So I will present you like the classical treatment for deriving what we call the inverse quantum power, and then actually you can derive also the full process and the inverse quantum power in a full QED context. So let's try to see first how we can derive the main feature of the inverse Compton scattering classically. So then what we are studying here is how an electron will react by the scattering with an electromagnetic wave. So whenever you have an electron that is subject to an incoming wave, the electron is accelerated. So we have to understand how a radiation field can be generated by a moving charge. So then let's see the basis for the creation of a radiation field. So if you have so let's suppose you have a charge which is moving along a trajectory. And this is a charged particle, so it's moving along a trajectory. It has a given velocity beta, which is tangential to the trajectory. And you can measure the position of the charge at different time, t and t prime. And this moving charge does source a radiation field. So if there is an acceleration in this direction, then if I want to measure what is the radiation field at a given distance r generated by a charge which was in the position small r at time t, I can do so by understanding what is the radiation field that is generated by this moving particle. So at the observer, the field that is produced will be the field that has been produced at time t prime, which takes into account the fact that the radiation had to propagate with a finite speed. So this can define then the retarded time, which we call t tilde, and that we will use. So if one starts from the Maxwell equation and try to solve with the retarded time solution, then one can show that there is an electromagnetic field, there is an electric field that is generated, and this electric field takes different terms, so I write them here. So there is a first term which is related, it's called the velocity field, and it recovers the Coulomb potential of this charge. So with the classical dependence of 1 over r square. And everything should be evaluated at this retarded time. And then there is a second term, which is the acceleration field, that comes from the fact that this particle is moving with a non-null acceleration. And it goes like 1 to the r, and where by beta is the beta factor of the particle, k is related to the direction of the acceleration, the velocity, and the normal to the direction at which we want to measure the field, and which is this r here. So this is the velocity field, this is the acceleration field. What we are mostly interested in high energy astrophysics is what is this acceleration field, because every time that we have an accelerated particle, and this we will have often, for example, in external magnetic field, but also in high energy astrophysical emitters, then we have to know how this accelerated charge can re-radiate. And this is what we are mostly interested in, also to derive the inverse Compton power. Yeah. So this is what we call the retarded time. And this is the solution to this equation here. So let's consider the non-relativistic case where we only have the radiation field. So we don't have, we only have a radiation field that is, or if you want, the accelerated part, the acceleration part of this electric field. So just to have a look at the geometry, so you have this acceleration. This is just in another direction of this diagram. You have the acceleration vector. You have the normal to the direction at which you want to measure the position at which you want to measure your field. And what it happens, as I mentioned before, is that because this charge is accelerating along a trajectory, that what is sourcing is an electric field which is orthogonal to the normal, and then we will see why. And we are interested to understand what is the radiation that crosses the area, the infinitesimal area, element of area. So if we just consider the radiation field, so the second part in this sum, then we can show that in the non-relativistic case, I will put back the C just for convenience. So what we see here is that the radiation field, so the second part of the sum, is perpendicular to the normal, to the direction of at which we want to measure the field. And we can also see that we also have the magnetic field that is associated to that, because of the fact that the B field can be defined as the cross product between the sourced electric field and the normal. Then we have that they do have the same modulus, which depends on the acceleration and on the angle phi between the direction of the field and the acceleration. Okay? Yeah. Sorry? Because this is what we are interested in if we want to understand what is the electric field that is re-radiated by the source. So for the following applications, I'm just interested to see what is the electric field and the magnetic field associated to the second term, because more often this is what will matters, and this is what will matters in the inverse Compton. As a matter of fact, the first term will give you a Coulomb potential. So what you can compute is then what is the flux which is carried by this wave, and this is by definition what is called the Poynting vector. So the Poynting vector by definition is the cross product between the electromagnetic, the electric and the magnetic field divided by 4 pi. And in this case, because in the non-relativistic regime and when we only consider the radiation field, is the modulus of the radiation field to the square, and the Poynting vector will be also orthogonal to the radiation field. So in general, you can define what you are interested in is what is the power, so what is the energy that is re-radiated by this moving charge. Do not forget, everything starts from a charge which is accelerated, that creates an electric field because of this acceleration component. And so what you are really looking for is what is the power which is emitted by this charge that is flowing across the elemental area. So this is the flux, the Poynting vector times the area element. And the area element, if you remember, so there is an angle, so this defines the solid angle delta omega, which is related to the area as r square the omega. So then and the Poynting vector we have seen will be just the modulus of the Poynting vector times its normal. And the modulus of the Poynting vector is related to the modulus of the radiation field. What is missing? An arrow? The area element is missing an arrow? No, it's here. Better? Okay. So then we can compute, I will drop we just take the normal direction. So we want to know what is the power per unit angle, and we can show that just from the definition of the modulus of the radiation as a function of the acceleration. This is the equation from the power, which is emitted per unit solid angle. Then you can integrate over the angles. So the total emitted power averaged over all angles for an accelerating charge is proportional to the square of the acceleration. And so this is the Larmor equation for a single accelerated charge of charge Q. And this will be used both for the inverse Compton and the synchrotron power. Yes. And then you integrate this sin square of phi in the phi, and you get something that then will lead to 2/3 with the 1/4 in front of. We are computing the power. We are calling, this is the total power. Sorry? Yeah, but I think it was like the. Is in the same direction of the power.
Normal vector or just I mean, of course, it's a scalar, but yeah.
I have to look it up.
But your draw is perfect.
I have to look it up where I have to put the vector here. But I think it's.
The point vector, right?
Yes.
And the elemental power.
It's pointing to the normal. Yeah. Yeah. And because it will then get it rid of here. to the air. But okay, I think this is not a point. I will just look it up exactly how to use the correct notation with the vectors, and I'll tell you tomorrow. But main point is that indeed the power is a scalar, and that's the equation for the power. Yeah. No, I agree. It comes from the area that is normal to the direction of the propagation of the pointing vector, and so we'll then get to 1 with the normal vector. Okay. Other questions? If not, then let's go ahead with the inverse Compton calculation. So this is the Larmor equation, and for an electron, okay, you can then specify in function as a function of the mass and the electron charge, because so let's go back to the main point. You have an electron which is accelerated by an incoming electromagnetic waves. So then back you can express the force that is acting on the electron as the Lorentz force, and then you can get the acceleration as the ratio between the Lorentz force and the mass. And so as a matter of fact, you can, in the presence of this electric field, the acceleration is nothing else than the electron charge divided by the mass times the electric field, and is accelerated. The acceleration has the same direction as the electric field of the incoming electromagnetic wave. So what we are interested in is to know what is the power that is re-emitted by this electron because of the effect that is accelerated. And so this power, again from the demonstration above, is related to the charge of the. So here I'm just replacing the expression for the acceleration in terms of the acceleration that we have derived here. So in general, if you have, for example, a sinusoidal wave of your incoming radiation, then what you can get is the time average power. I'm averaging over this sinus of omega. So the interpretation of this is that you have this radiation which scatters off this electron, and this electron then re-emits power. So in the scattering theory, you can see it, I mean, you can define the cross-section of this process as the ratio between so the scattering, the cross-section for this process to happen is by definition the power which is radiated and the incoming flux. So the flux, so again, this pointing vector. So the modulus of the pointing vector average over time. And if you remember, okay, the definition of the pointing vector and its modulus, in this case, again, we have the magnetic field associated to this radiation is basically the same amplitude as so we assume that as the same amplitude as as the electric field, then the average the time average Poynting vector, we take its modulus, is E0 squared divided 8 pi. Now I'm not sure about the 8, but fine. Okay, so this is the average power times, yeah, and it times and so we can show I'm just wondering if I made it wrong. Okay, no, it's correct. Okay, so that's then is the cross section for this process, and for the electron, this defines what we call so this cross section for the case of the electron is what we call Thomson cross section, which is a cross section that comes often in high energy astrophysics and has an important value. So the numerics is 6.65, which is not important. The order of magnitude is minus 25 centimeters square. So this is a number that in this kind of processes often occurs, and we have seen already yesterday that there are limits for the gamma-gamma per production cross-section, where numerically you find something that is similar to the Thomson cross-section. So if we then look at the final expression for the power from inverse Compton, we can then have that the time average emitting power is can rewrite it as Thomson cross-section which we can also show that this incoming electromagnetic wave has an energy density. This energy density, by definition, is the sum of the square of the moduli of the electric and magnetic fields. Okay. So now we want to understand how we can then write what is the power. So we are interested again in gamma electron to gamma electron. So what we are interested in is to understand what is the total energy loss of this electron, which will correspond to the energy gain for the photons. So this is the total re-emitted power by the electron. So now we want to go and understand what is the total power of the photon. So I think there is a factor of 2 somewhere that I missed, but I'll double check. Okay, so what we have is this equation for the power expressed as a function of the energy density of the photons. Now, this is a very generic expression because the power is like an energy divided by a time, so they do transform the same way under Lorentz transformation. It means that this kind of expression should be also valid in the case in which you have an electron which is moving with a given velocity, so with Lorentz factor gamma and beta. And this should be also, yeah, yes. So what we calculated is the power that is re-radiated by the electron, which is not the total power the electron can lose. Yes, but then you also have to take into account, yes, but what we are interested in is the power that is a change in power of the photons, because we are interested finally in the re-emitted radiation. So what I'm showing now is how to compute the inverse, so the power that is that goes into the outgoing photons, which will be the relevant one to compute the inverse Compton radiation. So in the rest frame of the electron, it also holds this relation where in this case we have the energy density in the electron rest frame, and energy density does transform this way under Lorentz transformations, where again this angle is the angle between the incoming photons and the electron velocity. So then there is always a dependence on this angle psi. We want to get rid of it, so we can average over the angles distribution. And this holds for an isotropic radiation field with cop psi distributed between -1 and 1 uniformly. So what we are interested in is the energy loss rate, which is equivalent to the inverse Compton power. And since the initial incoming radiation is carrying energy, the total inverse Compton power will be the difference between the incoming radiation, the power carried by the incoming radiation, and the power that is re-radiated. So will be the difference between the outgoing radiation, because we are interested in it, and is an energy loss term, minus the incoming radiation. So this gives you the total power that is radiated from inverse Compton. And if you just do the difference, you end up with this expression, which is very generic. And it is valid for the inverse Compton if this is the energy density of the radiation field. But in very generic terms, you have that whenever you have an interaction of a photon with an electron that re-emits some photons, being this photon real or virtual, then you have always this expression for the power of the re-emitted radiation. Or if you want the energy loss rate associated to this process. So there is another process that we will see in the following, which is synchrotron emission, which can be understood in the same way of inverse Compton. If instead of a real photon, you have a virtual photon that is sourced by an external magnetic field. And the energy loss rate or power will have the same expression, but while for the inverse Compton, this is proportional to the radiation field. for the synchrotron that we will see later, this will be proportional to the magnetic energy density. But in very general term, this is the most general expression for the power that you can have. So the power as units of ergs over second. And sometimes what you often find is actually the differential power as a function of energy, or the differential power as a function of frequency. So once you have this generic expression for the power, what you can compute is if you have a generic particle spectrum of injected high energy particles, which has a given power law, then you can ask yourself what is the behavior of the total inverse Compton power, and this will be also a function of the particle energy distribution spectral index. So this n is the number of particles per centimeters cube differential in energy, if you want. And you can recast it. You can also use, instead of the variable E, you can use the variable K, gamma, sorry, so the Lorentz factor. And again, in terms of Lorentz factor, this will be proportional to gamma to the minus x. So then the total inverse Compton power should be the convolution between the inverse Compton power emitted by a single electron and the particle distribution. You can integrate over gamma, assuming that there is some range of validity of this particle distribution. And this will be proportional to a power of gamma, which is related to the initial particle distribution. So point is that the inverse Compton power for a given distribution of electron energies will carry the information about the parent electron distribution. So often what we will measure is radiation, we will see in a bit, that is related to the inverse Compton. So from the inverse Compton flux, which is related to the inverse Compton power, then we can go back to the initial distribution spectrum of the primary particles, which is in the end what we are interested in. Okay. So now that we have seen the classical treatment for the inverse Compton radiated by an electron, then what we can have a look at is the full QED treatment, from where you can derive, again, the same quantities and have a more general application also to the full relativistic regime. Okay. Okay, so the classical limits that we have seen so far was for beta of the electron smaller than 1, which also translates to a constraint on the energy of the photon smaller than the mass of the electron. But in general, what we should consider is the full QED process of an electron scattering elastically of a photon, or a photon scattering elastically on an electron, where you have two different diagrams. And I will not derive the cross-section for the process, but this was done in 1929 by Klein and Nishina. Okay, so they worked out the full cross-section in a QED formalism, and this is known as the Klein-Nishina cross-section. I will write here. This will be also in the notes, so if you don't want to write it down, that's fine. Which is related to the energy of the incoming photon, the energy of the outgoing one, and the angle between the direction of the outgoing photon and the incoming one. So let's consider the electron rest frame again. You have an incoming photon with energy epsilon and momentum k, and this then get rescattered with an energy E gamma, momentum k, okay, ki, k final, and this is the angle between the outgoing photon direction and the incoming photon, which is kept track of in the expression of the cross-section as a function of angles or solid angle. So then one can integrate over the solid angle distribution and get the total Klein-Nishina cross-section, which will be a function. So we can get rid of the angle by integrating over the angle a variable, and then this Klein-Nishina cross-section will just be a function of the ratio, as you can see there, between the energies, and we can call this x, so we can redefine this x as the ratio between the incoming energy as the mass and the mass of the electron. So this is just like notation. So one can see that the Klein-Nishina cross-section has two different limits. You can see here the sigma Thompson that is appearing, right? So when this ratio, so when you are in the limit of x smaller than 1, so the incoming energy of the photon smaller than the mass of the electron, the Klein-Nishina cross-section tends to the sigma Thompson. While if you are in the fully relativistic regime, which we call extreme Klein-Nishina, then the Klein-Nishina cross-section goes about as sigma Thompson divided by x times the logarithm of 2x plus 1/2. So those are two regimes that appears often, once when we are fully relativistic, and the other one where we are in the Thomson regime. So now let's have a look at the kinematics of the process. So there you have the momenta and the energies that are involved, and what we are interested in is to understand what are the typical energies of the outgoing photons, because remember what we have is this process. So given a distribution of electrons and given a distribution of target radiation field, what we want to understand now is what is the average or typical energy at which the photons are scattered. And we will see that those are up scattered at higher energies, what is the final energy of the outgoing photon in the observer frame, it's what we are interested in. To understand if you have a population of GeV electrons impacting onto the CMB of the radiation field of the galaxy, at what typical energies do you expect the inverse Compton radiation to happen? Okay. So then we have to work out what is the kinematics of that process. So we can work with 4 vectors and requires the conservation of the energy momentum of the process, where K refers to the photons and P refers to the electrons. And we are working, so this is a process that involves on-shell particles. So again, we know that the mass, there is a condition on the 4 momenta squared for the mass of the electron, and same is for the mass of the photons, which is massless. So it's for the 4 momenta of the photons. So now in the electron, the electron rest frame, let's have a look at the case in which the electron is at rest and there is a photons that is scattering off this electron in the electron rest frame. So in the electron rest frame, we can express the 4 momenta explicitly. So the incoming energy, the energy of the incoming electron is epsilon. And let's consider that we are basically considering the kinematics and the momentum distribution as it was in the sketch. So the final photon will be rescattered with an energy, a final energy E gamma at a given angle theta with respect to the incoming photon. Okay? So then we go back to this expression. In the electron rest frame, we can, let's look like this. We can expand that expression. Okay, we can just consider the final, what is the quadrimomentum of the electron, of the final electron. Just from there, we can rewrite it. Okay, and then we can consider the square of this expression. Okay, so we'll have to do the cross product between these 2 vectors, I mean these 2 terms. Okay, and by using the on-shell condition in the center of mass, in the electron rest frame, then we can show that the energy of the outgoing photon is a function of the energy of the incident photon and the angle. Okay, so this is by using the explicit expressions of the momenta, of the quadrimomenta, and developing this product here. So first thing that you can notice is the energy of the final photon is close to the energy of the incoming photon. And there is only a slight variation, and the variation of the energy of the photon is proportional to the ratio between the incoming energy of the photon and the mass of the electron. So the fact that the photon is only slightly changing in energy tells you that this process is a process where you will have a continuous energy loss. So it's not a catastrophic loss, but the energy of the photon is only mildly affected by the scattering. And what is important is the energy that is re-radiated by the scattering, at which final energy you can find this photon. So this is in the electron rest frame. So now to find the typical frequency at which these photons are re-emitted, we have to go into the lab frame. Okay? And we are again considering what we have seen yesterday, so that there is a transformation between the two frames. I'm gonna prime the electron rest frame energies, and we will consider the lab frame where we have unprimed variables. Okay? So in the relations for the Lorentz transformation, I gave them yesterday. We can first of all consider what is the energy of the incoming electron incoming photon in the lab frame, and this is related to the energy of the incoming photon in the rest frame by this relation here. Psi is the angle between the velocity of the electron and the incoming photon in the lab frame, and gamma and beta refers to the electron velocity. So likewise for the final outgoing photon, the energies are related to the center of mass frame this way. Well, where here we will have another definition of angle, because this time this is the angle with for the outgoing photon with respect to the electron velocity. So by considering the general expression for the photon energy in the electron rest frame, we can then, and this transformation here, we can get the final expression for the energy of the photon in the lab frame, which one can work out with the different angle, and there are expressions between the angles that are known as aberration formulas. Point is that after a bit of algebra, what is most important is that this holds in the limit where x is smaller than 1, so we are in the Thomson regime. What is very important for you to retain is the typical behavior of the energies. So given an incoming photon with energy epsilon, then the energy of the upscattered photon is proportional to the square of the Lorentz factor of the electron. Okay, so why this is relevant is because you can then have some idea of the numbers at play, which is what we are mostly interested in. So in the Thomson regime and for an isotropically emitting outgoing radiation, so this we can show that this equation holds true. And if we plug in the numbers, So to have some quantitative idea of the energies at play. Okay. That's the very important point. So if you have inverse Compton from a population of electrons onto a radiation field, then what you have is that the energy of the outgoing photon goes as the square of the electron energies, so meaning that it can rise pretty quickly depending on the energy of the primary population. And for typical radiation fields in the galaxy, you can have photons at different energies. So let's have a look at the typical energies of the photon fields in our galaxy. Yeah. So first of all, you are in the okay, you are on the relativistic regime. So is that expression, okay, is there, and then you have to average over the angle distribution. Okay, so you average is the average over the angle distribution of the outgoing and incoming photons. Yes, so let's have a look at a more quantitative aspects of the problem. We have seen yesterday that for the CMB, the typical energy of the radiation is about 10 to the minus 4 electron volt. For the infrared, this is rather 10 to the minus 3. And for the optical, this is higher energy, so is about 0.3 electron volts. So now if you have electrons with typical GeV energies, you can check that for the CMB will upscatter photons mostly in the KeV band. The infrared will upscatter photon in the soft gamma ray band, and the optical has slightly higher energies, but always in this kind of regime. So now you increase the energy of the electron to TeV, and you shift the radiation that comes from inverse Compton to higher energies, because it goes as the square of the energy of the electrons. So point is that whenever you have an electron population of cosmic rays particles in the galaxy, those particles do have a particle distribution function in energy, and so you can predict what is the final distribution in energy of the upscattered photons. And the scattering probability, the full scattering probability, is given you by the cross-section, the Klein-Shina cross-section or the Thomson cross-section, depending in what regime you are.
Produce some quantity of photons more energetic than the source.
Yeah.
But
yes.
the likelihood of happening
The probability is given you by the cross-section. The cross-section describes you what is the probability of one photon or energy epsilon to interact with one electron of energy E of E. This cross-section is to which kind of environment are you referring to? Because you have the electrons and the environment is the radiation, is the radiation field. So it is an environment effect. Okay. So, and it perhaps now I will write you the full expression of the flux and how the probability of interaction kicks in the final flux expression will make clearer what is the dependence. Okay. So in general, in the galaxy, we have fluxes of cosmic ray electrons. We'll see later how they can be accelerated in galactic sources. But let's consider the fact. So let's start from the fact that we have a position-dependent flux of the cosmic ray electrons in our own galaxy. So this is the cosmic ray electron differential flux. I think we have seen also yesterday the definition and the units, but let me put them there again. So you also have sometimes you have the number densities of these electrons which are related. But so then let's consider the emissivity. So what is the photon local emissivity due to this process when you have a population of electrons in the galaxy? So the local emissivity, the differential emissivity in energy will depend. Someone say something? No. Will depend on the position in the galaxy and on the energy at which we are interested. So this is a steradian term, and it is the convolution of the target So this is the target radiation field density times the probability for this scattering to occur, which is a function. This is the full Klein-Shina cross-section differential in energy, which is a function of the energy of the electron, the energy of the radiation field, and the energy at which we are interested in computing the emissivity. And this, of course, depends on the flux of incident particles, so of the flux of primary particles which are the electrons. Okay? So then for each radiation field, you have the probability of, so the emissivity will depend on what is the probability of the radiation to scatter off that specific part of the radiation field. And more generally, the product between the cross-section and the radiation field density, as we have seen before, is inverse Compton power. So often you might find the emissivity, the inverse Compton emissivity of an electron population to be written as a function of the inverse Compton power of the electron, where we have seen before the inverse Compton power depends on the cross-section and on the energy density. So if you remember before, we had the power was proportional to the Thomson cross-section times the energy density of the radiation. And here, this is just the more generic expression in the fully relativistic computation, where this inverse Compton power is directly a function of the cross-section and the energy density. And this, in order for the units to be right here, this P tilde is the differential power as a function of the energy. So if you have an electron population, so like long story short, if you have an electron population in the galaxy or in whatever astrophysical environment you are considering, in order to compute what is the emissivity, or let's say the final flux of photons that comes from interaction of this electron population with an underlying lower energy radiation field, then you have to compute to know what is the energy density of the radiation field, what is the cross-section for the process to happen, and what is the initial flux of primary electrons. And in this case, you can then compute, we have seen yesterday, how to go from the local emissivity to the final gamma ray flux, right? So the final gamma ray flux that we observe will be related to these fundamental quantities that in a classical treatment can be like derived from simple scattering theory. So perhaps let's have a look at how the inverse Compton in the galaxy looks like. So if you were to start from a typical distribution of electron in our galaxy, then there are like, you can use numerical prescription to implement these kind of integrals, where this cross-section again is the Kleinian cross-section, and you can predict what is the spectrum and spatial distribution of your radiation. So now, might be a bit pedantic, but what is really important to keep in mind is that whenever we are dealing with high energy, let's say, with whatever energy band in photons for observations, what you can measure is what is most of the experiments being done on a satellite or telescopes at Earth. You can measure photons as events that have an energy and a direction in the sky, right? So then you can project the number of photons into different planes. So if you project them by integrating over a given region of the sky, like the full sky here, you can get the flux as a function of energy, and this is what we call spectral energy distribution of a given radiation. And here the inverse Compton, what I want just to focus now on, is a red line. But what you can also do, and this is possible thanks to instruments that can survey large portions of the sky, is that you can also measure what is the distribution of photons in space. So in directions along the sky, which are characterized by the galactic coordinates. And likewise, you can predict, since you have the full energy, the full angular distribution of your signal, what is point by point in the galaxy the expected photon flux. And you project it into the galactic coordinate, so L and B, and you have what we call the spatial distribution of the photons, which sometimes we also refer to as morphology of a signal. So the morphological imprint of a radiation or a process and the spectral distribution of the same process are two observables that we use a lot when we want to analyze real data. Okay? So you can, and then there are, whenever you look at a spectrum or at the spatial distribution of a component, so this is the inverse Compton, what I'm saying is valid for everything we will see in the following, there are like characteristic features that distinguish one process from another. So if we look at the spectrum, here are other components, so other emission processes that can produce gamma rays in the GV band. And the spectra are different and depends on whatever ingredients enters in the definition of the flux. So we will see tomorrow why, for example, when producing photons from pi0 decay, you expect what is called a pion bump at around a few GeV. And here the inverse Compton spectrum directly traces the energy dependence of the primary electron flux. So by analyzing like the gamma ray sky and or whatever band in the photon fields and understanding what are the processes that contributes to that and try to disentangle them, then you can go back to the properties of the primary particles that have induced, in this case, the primary electron population. So now let's suppose these are supernova remnants in the galaxy, then the spectrum of the inverse Compton is directly related to the particle injection spectrum of electrons from supernova remnants or pulsars. But if these electrons are due to dark matter, then the inverse Compton give you a leverage to go back to the primary particle distribution from whatever dark matter or BSM physics there was. We will see that in the following, but it's just to give you an idea of why I'm spending time on the inverse Compton. So likewise, there is in the spatial distribution of the photons, there is a lot of information. Because you can keep track of the spatial features of the different ingredients. So the spatial distribution of the photons in the case of inverse Compton, but for the other processes we will see there are other spatial information that kicks in, depends on what is the spatial distribution of the target radiation field, which will be the most intense we have seen yesterday towards the galactic center, and then will be less and less intense going away from the galactic disk. This is because in the disk we have strong optical and infrared emission from the stars, while at high galactic latitudes we only have the CMB. So the shape of the inverse Compton directly trace the shape of the target photon density. And this will be the same for the protons that we will see tomorrow. The final distribution of the photons from pion decay will directly trace the distribution of the target protons, because this comes from PP. So the spatial distribution of the final radiation encodes the information and traces the information of the target and of the primary population that induce that kind of mechanism. Okay. So there is a second important mechanism for producing radiation from a population of electrons, which is the synchrotron radiation. I told you before that we can interpret the synchrotron emission as the scattering of a virtual photon, which is sourced by an external magnetic field onto a cosmic ray electron. So one can work out the power with different treatment, either with a full QED treatment where you have a virtual photon instead of a real photon, or in a classical treatment. And the classical treatment starts from what I mentioned yesterday about the Larmor radius, that so the fact that when you have a particle in a magnetic field, this particle then, a charged particle then gyrates with a given Larmor radius, and while gyrating, since a particle that is on this helicoidal motion is accelerated, then since this particle is accelerated, then it sources an electric field, as we have seen this morning. So whenever there is an external field and you have a charged particle, there is always a radiation field that is associated to this accelerated motion, okay? And the power of the radiated field is the synchrotron power, which is in the classical limit is what we have seen this morning, where instead of the radiation energy density, you have the magnetic field energy density, okay? So then the question is, okay, but this we have seen is valid in the classical limit, so for the power of the synchrotron to be generically following this expression, we have to be sure that the typical frequencies at which the synchrotron is emitted is indeed always valid in the Thomson regime. So one can compute the typical frequency of the synchrotron emission. So for the synchrotron, I will give you like the final equation. I won't rederive everything for the sake of time. But the typical frequency of the synchrotron is related to the radius at which this particle follows the helicoidal motion. So is related to the angular gyro frequency, which in turn, again, if you remember from yesterday, is related to the charge, to the magnetic field, if we are considering a uniform magnetic field, and to the mass of the particle. Okay, so one can, from this expression here, as we did for the inverse Compton, we are interested in understanding what is the typical energy of the synchrotron re-emitted power. And one can show that this, again, depends on the ambient parameters. And it goes as it was for the inverse Compton and the gamma squared of the electron. So for typical electron energies in the GeV band and magnetic field in the order of microgauss, then the energies of the re-emitted synchrotron are in the microelectron volt, 200 of a microelectron volts. So the frequency falls into the band of gigahertz, megahertz to gigahertz. So this is the band of is the radio band typically. So whenever you have an electron population of GeV energies, you produce two types of radiations. One is the inverse Compton in the, let's say, soft MEV band, and the other is a synchrotron radiation from the same electron population in the radio band. And those two processes are linked by the target density of the radiation field and mostly from the initial parent population. One will depend on the radiation field, so the inverse Compton, and the other depends on the distribution of magnetic field, so what is the galactic magnetic field distribution. So you have a truly like multi-wavelength, if you want, signature of a population of electrons in the galaxy.
In this case, the target would be the photons in this
magnetic field. Yeah, are the virtual photons that are sourced by the galactic magnetic field. So, and likewise, if you consider, so this is the synchrotron from one electron, then you can consider the synchrotron from an electron population, and in the same way as it was for the photon, for the inverse Compton, again, the slope of the total synchrotron power traces the slope of the energy distribution of the primary electrons. If we want then to derive the analogous expression for the local emissivity for the inverse Compton, and we do that for the synchrotron. Typically, so we are in the radio band. So in radio band, we don't use energies, but we use frequencies. So we are interested in the local emissivity as a function of frequency differential in frequency. So this is differential in frequency and said to be differential in energy. And again, the local emissivity is a convolution of the synchrotron power of a single electron times the distribution or spectrum of the primary cosmic ray electrons, where this synchrotron power is the differential synchrotron power in energy, and this synchrotron power has a specific shape. So it has two regimes. At low frequencies, it rises as the frequency to the 1/3. It peaks at a critical frequency, which is about this frequency that I show you there. And then it decreases with an exponential behavior. Okay? So then your flux, your final flux will be a convolution of the frequency dependence of the power of the synchrotron by one electron and the spectral energy distribution of your primary electron population. So in radio, rather than fluxes of particles, since we are looking at radiation, people use the definition of brightness temperature. So it's the temperature that corresponds to a given intensity. And so you might find in radio papers the definition that instead of plotting fluxes, we work with brightness temperatures, when putting back the C and other constants. This is related to the intensity in this way, just for you to orient yourself when you might encounter plots like this, where this is the temperature brightness of the synchrotron emission by population of cosmic ray electrons in our own galaxy, scattering off the different components of the magnetic field as a function of frequency. This is, as I mentioned before, peaked at around like 100 megahertz to gigahertz when we have a GeV to TeV electron population. And the spectrum that the synchrotron emission follows is again like a featureless power law, where the slope of the power law mostly depends on the slope of the incoming of the primary electrons. On the other hand, if we look at the morphology of the signal, the shape of the photon distributions, of the synchrotron photon distribution, traces the shape of the magnetic field structure, which is way more intense in the disk and then fades away at higher latitudes. Okay, but it's very different from the shape of the inverse Compton, and this is because in this local emissivity equation, the synchrotron power depends on the magnetic field structure. Okay. There is a peculiarity of the synchrotron that I just want to mention, but I won't have time to go into the detail, is that there is a third observable for like photons, which is the polarization. So photons might be polarized, and depending on the process that is leading both to the production and, mostly to the production of the photons, you can have highly polarized emission. The synchrotron is one of such emission mechanisms because synchrotron radiation from electrons always lead to highly polarized final photons. And this can also occur in gamma rays through other mechanisms, and polarization is one of the new avenues to try to leverage upon in order to disentangle emission mechanisms and also look for new physics. So I want to mention it because it might be something interesting to have a look at in the next few years. Okay, so I'm done basically with the interaction with radiation, between particles and radiation. Tomorrow we will see what are the interactions between particles and matter, and we'll go ahead in understanding the contribution.
Why is not so, say, symmetrical?
This is because of the magnetic field structure, and the magnetic field structure is highly asymmetric. So there are different reasons. One is that the way in which you measure the magnetic field is through pulsar measurements, polarization measurements, and as a matter of fact, the sample is not complete. So there is a part which is like a systematic effect. There is another part which is really that the distribution of magnetic inhomogeneities is not symmetric in the galaxy. So depending on where the stars are, the cosmic ray sources are, you might have asymmetries in the magnetic field distribution. Welcome.
The intensity of the photons.
So these in I have it here. So these intensities